Welcome to the UGC EPG Pathshala lecture series in computer science. In this series of lectures, we have been talking about database management system. For today's session, I will be discussing on multimedia indexing techniques. To basically understand about multimedia indexing techniques, let me just give you a gist of why this indexing required. As you all might know, multimedia means various media elements. It could be audio, video, text, image, even biometrics. All this could be a component of this media. So, in such cases, say for example, for a geographical positioning system or a geographical information system, we might have to locate the spatial distance between two different locations. Say for example, I have a query by where I just need to identify after getting down on an airport or at a railway station. The major destinations that I am searching for would be what would be the restaurants or hotels in 2 kilometers around the railway station. So, in such cases, the system has to understand what are the hotels that is available in the around the railway station for the given distance. For those cases, we might need the appropriate places, the location and other details. So, with this as the preliminary information, we will start looking at the indexing techniques. The learning objectives for this sessions include understanding multimedia data structures. So, we will talk more on the multimedia data structures. At the later half of this particular topic, maybe I will tell you where it can be applied. We will be looking at a specific data structure which is called KD trees, which is supposed to be k dimensional trees and their node structures. To be very specific, this k can be denoted in terms of 2 dimension. So, 2 dimensional tree operations. Further, we will talk about the enhancement of 2D trees, which will be point quad trees, MX quad trees and a totally different notion which is supposed to be an R tree or region trees. To start with, why this multimedia data structure? As I have told you, when we started collecting this geographical data, the different media elements, the important source of these media data is geographical data. So, any geographical information system stores information about physical region in the world, maybe in terms of points. We can take out the example of how we have drawn a graph and located a particular city or a town, where we have positioned it in the xy coordinates and we fixed up a point. So, this we call it as a map. A map is just a 2-dimensional image and certain points on the map are considered to be of a greater interest for us. So, these points are then stored in one of many specialized data structures. Maybe as I have told you in the objectives, it could be either in the form of a 2-dimensional tree where the k is defined, or it could be 3D trees or 4D trees or n dimensional trees. The other thing that I will be talking about for today's session would be on a point quad trees, MX quad tree and R trees. Supposing you consider this as a map, this is a geographical information system about on a particular area. So, I have given 2 different distinctions here. One is a map with marked points and a map with marked regions. What does it mean? Say for example, in a specific area, I have marked a particular location by a point which is indicated in red and several points that exist. At the same time, this point can be a building, can be of a larger location space. So, instead of locating it as a point, when you appropriately wanted to locate with a fewer distance from the space, It can even be projected at a larger component. So, we may plot it in a region. So, these are the two things that we are considering as an example. The first dimensional trees, first dimensional data structure that I will be talking about is on the KD trees, which is used to store k dimensional point data. So, it is not used to store a region data, it has to more do with the point based data. So, a two dimensional tree where the k is denoted with a value of 2 stores two dimensional point data, while we can increase on the order of this k to 3, 4, 5 and so on. Talking very specifically on the two dimensional data structure, the node structure of a 2D tree will be of this form, where the node structure will have information x value, y value. In the information and x value, y value, where the x and y are supposed to be the coordinates, we will have two links, one is called a left link, the other one would be a right link. So, we are about to consider a limited portion on which whether the node that is to be inserted, whether it should be on the left hand side of the node structure or right hand side of the node structure is to be considered. So, we write a data structure for that, where the node type would be of a record type, informations will be of info type, x value is purely real, y value is real, left link will be a pointer to the node type and right link will be a pointer to the node type. So, this information field is any user defined data type. So, we can say it as a city or it could be a B, C, D value. X and y value denote the coordinates of point associated with this particular node. Left link, L link and R link are the 2 points to the two childrens, to indicate the two childrens. Let us consider the two dimensional tree. For this two dimensional tree, we have denoted that node structure. So, the level of node is defined in the usual way with root at level 0. So, we call the root node as level 0, because we are to consider insertion of multiple nodes at different levels. So, the definition of a two dimensional data structure would be of a 2D tree is a binary tree satisfying the following condition. If n is a node in the tree such that level of n is even, say the root node is supposed to be level 0, the node that I am supposed to insert would be of level 1. So, in that case what should be done, and if the node that I am trying to insert is of level odd, what should be done. So, I am basically looking at whether the level is odd or even. So, level 0, subsequently when I wanted to insert one more node, then it becomes level 1 node. So, if the node in a tree such that level of n is even, then every node m in the subtree, that means the node that I am trying to insert is the m node that is rooted at n dot L link. If it is to be rooted at the left hand side of the root node, then the property must be x value of the newly added node should be less than the x value of the root node, and every node p in the subtree rooted at n dot R link, if it is to be rooted to the right hand side, then the property need to be p dot x link greater than or equal to n dot x value. I repeat again more clearly on what this statement would mean. First, we will check for the level of the node. If the level of the node is even for this constraint as per this definition, if I am supposing I am inserting a node m, I find that the x value of the node that is to be inserted is less than the x value of the root node, then it is to be linked to the left. And if I am trying to insert node where I check a constraint of x value of the newly inserted node which is greater than or equal to the already existing node, then it is to be linked to the right. There is no concern on which acts as a root node. This root node consideration is purely user defined. And same is the case when it comes to odd. It will be vice versa, where I will check for the y value. If n is a node in a tree such that level of n is odd. So, previous case what we have defined, it was all for even node where we have checked on the x value. Now, we are purely considering y value, since because we are looking at the level as odd. Then every node m in the subtree rooted at n dot l link has a property that m dot y value less than n dot y value, which exactly means if I am supposed to insert node m where the root node is n, I find the y value of this particular node is less than the root node, then it should be branched left. Whereas, when I try to insert another node p where I have checked for a constraint, the y value of this p node is greater than or equal to the root node's y value, then it should be branched right. So, that is what this property is indicating. I repeat the sentence: if n is a node in the tree such that level of n is odd, then every node m in the subtree rooted at n dot l link has a property that m dot y value less than n dot y value, and every node p in the subtree rooted at n dot r link has a property that p dot y value greater than or equal to n dot y value. So, by looking at these two conditions, I will try branching the nodes, where I will check for, initially I may have to check for the level of the node. I will see whether it is odd or even. When it is even, I will check for the x value. When it is odd, I will check for the y value. Then the constraint are as defined. And what happens in case after having completed the complete tree structure, there is a possibility of insertion and deletion that can happen to the node. What happens to the subtrees that are rooted to the entire tree structure? To insert a node n into the tree pointed to by t, we may have to undergo a process like this. Check to see if n and t agree on the x value and y value fields. If it is one and the same, if so, just overwrite the node t, that is it. Else, you branch it to the left if n dot x value less than t dot x value, where this t is supposed to be the node that we wanted to insert, and branch right otherwise. So, if suppose I wanted to replace a particular node with the same value, then I can directly replace by erasing the existing value. If not, then I will check for the same constraint what I have defined earlier. I will check for the x value of the newly inserted node. Then if it is found to be less than, then I will branch it to the right. Suppose p denotes the child what we are about to examine. If n and p agree on their x value and y value fields, just overwrite the node p. That is it, we are done. Else, branch it to the left if n dot y value less than p dot y value, and branch to the right if n dot y value greater than or equal to p dot y value. So, we may have to repeat the same procedure again and again. So, branching on x values, we are at even levels in the tree, and branching on y values, we are at the odd levels in the tree. So, we will temporarily perform an insertion operation by considering an example. Suppose that we wish to insert the following points like Tiruchirappalli, Tanjavur, Mannargudi, and so. We will consider this map and we will insert all the nodes. What happens after insertion? Instead of looking at the entire region, now that I am trying to partition the region into two. Why? Because I have defined the k value as 2, and my k value says, and the two dimensional data tree value says it is all binary. So, x and y is partitioned in only by two, one as x value and one as y value, or left link and right link. In that specific case, I would like to split the region into two halves by marking appropriate location called Tiruchirappalli. So, if this is Tiruchirappalli, then I will try dividing the links of or the node structure into left link and a right link. So, initially I try to insert a node. Now that assume Tiruchirappalli becomes the root node, depending on which I have inserted, I have just considered a node, then it has divided into L link and R link. Supposing that I wanted to insert one more node to the existing node Tiruchirappalli. That means I am inserting Thanjavur also. For alternate insertions, for every insertions that I try to do, I have to alternately perform vertical and horizontal region split, which would ensure that we concentrate only on that specific region. Whereby what I am trying to say is, having said Tiruchirappalli as the root node, now that we have divided L link and R link. Supposing that we wanted to partition the second node or this node into two, where it is called Thanjavur. Thanjavur is branched to the right of Tiruchirappalli link. So, this will already we have performed a vertical branch or vertical partition. Now that we may have to perform a horizontal partition. The third point that I have indicated is Mannargudi. So, Mannargudi is to the bottom, or it is to the bottom of Thanjavur. So, it will be branched vertically. So, now that I wanted to have a node called Thanjavur, this Thanjavur is horizontally fragmented. Now, it has got two divisions. Then I wish to insert one more node on top of it, then it becomes Mannargudi, which is split in a vertical fragmentation. So, alternatively, for every node that I am trying to insert, I will be drawing a vertical fragmentation in the beginning, then I will be drawing a horizontal fragmentation, then I will be drawing a vertical fragmentation, which gives me a clear indication of what region I am trying to concentrate, rather than the entire location where I can define on a particular location. So, this has indicated, or this has taken us through the insertion procedure. At the same time, we may have to understand the deletion procedure of a two-dimensional tree. Supposing T is a two-dimensional tree and x and y refers to a point that we wish to delete from the tree. Search for the node n in T that has n dot x value is equal to small x and n dot y value is equal to small y. If n is a leaf node, then set the appropriate field, that is L link or R link of n's part to nil and return n to the available storage. So, whenever we wanted to delete, we may have to follow this procedure. Find a candidate replacement node R that occurs either in Ti for I, which is an element of L comma R. Replace all of n's non-link fields by those of R, recursively delete R from the Ti links. So, what would happen in case if we wanted to have a candidate replacement nodes for deletion? So, the desired replacement node R must bear the same spatial relation to all nodes P in both TL and TR that n bore to P. That is, if P is to the southwest of n, which means in terms of the direction southwest of n, then P must be on the southwest of R. If P is on the northwest of n, then P must be on the northwest of R, and so on we go with. Since because we are talking on the spatial location, we have identified which is southwest and southeast, northwest and northeast. Continuing further, what we exactly mean from desired replacement node R must satisfy the property that every node M in TL is such that M dot x value should be less than R dot x value if level of n is even, and M dot y value less than R dot y value if the level of n is odd. So, as we have started with the procedure, it is all the same from the top till the bottom. We are considering x values when it is even, we are considering y values when it is odd. So, every node m in TR is such that m dot x value greater than or equal to r dot x value if the level of n is even, and m dot y value is greater than or equal to r dot y value if the level of n is odd. If TR is not empty and the level of n is even, then any node in TR that has the smallest possible x value field in TR is the apt candidate replacement node. But if TR is found to be empty, then we might not be able to find a candidate replacement node from TL. Not only that, now that we have identified a specific point and it is not a range, but what happens in case, as I have told you, a range need to be identified. Say for example, with the explanation that I have started with, when we land upon a specific area, we wanted to correctly plot out how long is the distance between a particular location and another location. So, a range query with respect to a two-dimensional tree is a query that specifies a point xc, yc, which says the coordinate distance and a distance r. The answer to such a query is a set of all points x, y in the tree, such that x, y lies with the distance d of xc, yc. That is, a range query defines a circle with the radius r centered at location xc, yc and expects to find all points that lie within this particular circle. Say at times I might say I am landed at a particular location and I wanted to find out any specific location around 2 kilometers. So, r is supposed to be 2 and any location that is surrounding 2 kilometers need to be correctly identified. In that particular case, this point becomes xc, yc and r is defined as 2 kilometers. Recall that each node n in the two-dimensional tree implicitly represents the region Rn. If the circle specified in the query has no intersection with Rn, then there is no point searching for this subtree rooted at node n. So, that stops with one level of tree which is called two-dimensional tree, which is very specific to a two-dimensional data element, and the node structure to that is completely binary, and the division has happened with either to the left hand side of the link or to the right hand side of the link, partitioning that into only 2, that is binary. Same is not the case when I try to proceed with points again, not a region, points again, but then I am trying to perform a quad trees. Quad means 4. So, instead of splitting the entire region into 2, I will try to split the region into 4, so that I can appropriately I can exactly say that it has all 4 directions, say northwest, northeast, southwest and southeast. So, any specific point that has been identified, if it is to be inserted to the tree, then I will perform the split into 4, so that I can identify all 4 regions. So, here comes the explanation about the point quad trees, where point quad trees always split the regions into 4 parts. In a two-dimensional tree, node n splits a region into 2 by drawing one line through the point, that is n dot x value and n dot y value, whereas in case of the point tree, the node splits the region it represents by drawing both horizontal and vertical line through the point n dot x value, n dot y value. Now that having clearly understood that the point is divided into 4, these 4 points are now called 4 different directions: northwest, southwest, northeast and southeast quadrants determined by the specific node n. So, each of these quadrants correspond to a child of node n. Thus, the quad tree nodes may have up to 4 children, rather than saying a conventional methodology of a two-dimensional tree where we could insert only 2 children. Here comes the data structure for point quad tree. The node structure is given in this form. Quad tree node type will be of record type, information will be of info type, x value is real, y value is real, and we have 4 directions: northwest, southwest, northeast, southeast, which are pointers to this quadtree node type. And we represent a node in this format where we say we have a specific point called node n, and any link that is to be routed to this particular node has n dot northwest, n dot southwest, n dot northeast, n dot southeast. So, if I am trying to represent a specific node, then that node is partitioned into 4 halves. So, any node that I am trying to insert, that can also be noted here. If I assume this as the root node, if I wanted to insert this particular node, assuming this as the root node, I have partitioned that into 4. If I wanted to insert any specific node, let me identify where that particular node is getting located. So, in this particular case, it is located to northeast. So, by locating this northeast position, I will partition that again into 4 quadrants. So, which exactly means this point lies in the northeast of this node n, and when I am trying to insert node m, which lies on the southeast of node n. So, that is how it needs to be clearly indicated. So, that stands the procedure for insertion in a point quadtree. The same when I am trying to delete the point quadtrees, the procedure that we may have to adopt for deletion of a point quadtree is something like this. If the node being deleted in the leaf node, deletion is completely trivial. We just set an appropriate link field of node n's parent to nil. So, any parent that is associated with this node is set to be nil, and return the node that is available for storage. So, as in case of deletion of a 2-dimensional trees, we need to find an appropriate replacement node for non-leaf nodes being deleted. In short, in this particular session, we have started with multimedia indexing techniques. I have started with k-dimensional trees, but then this particular session concentrate on 2-dimensional trees, where k is defined as 2. So, this is appropriately mapped to a map that is available with us for spatial location identification, and the major application of these multimedia indexing techniques were to the geographical information systems. If you take for example the 2-dimensional trees, these 2-dimensional trees are supposed to be binary trees having a specific node structure and a specific data structure, and when you look at the 2-dimensional trees, to build a 2-dimensional tree, we may have to initially check for the level of the node, and if the level of the node or the first node that is on the tree is considered to be level 0, any additions that happens to the level of the node will be considered odd and even. When the level of the node is even, then we will consider the x value of the actual node and the node that is to be inserted. If it is found to be less, then we might branch it to the left hand side of the node structure. If it is found to be greater than or equal to, then it will be branched to the right. And we have understood on the procedure of insertion and deletion on a 2-dimensional tree. Likewise, if the level of n is odd, we will compare the y value of the node that is to be inserted with the actual node. If it is found to be less, we will branch it to the left. If it is found to be greater and equal to, then it will be branched to the right. So, that procedure was made clear in the 2-dimensional tree, where it was only with 2 branches that we have done. So, it was all 2-dimensional trees. As an extension, we have gone for a point quadtree, where instead of dividing a particular image by 2, we started thinking about dividing in terms of 4, where we can appropriately represent the directions of the complete thing, because it was more towards spatial information. So, we have introduced another point which is called a point quadtrees, which clearly gives us a distinction of directions in terms of northwest, northeast, southwest and southeast on a same point, Now, it is not a vertical cross section, it is to the cross section both vertical and horizontal, and any point that is to be inserted will be appropriately located, whether it is on the northeast or northwest or southeast or southwest, then it will be divided into 4 quadrants. So, this 2-dimensional tree structure and 4-dimensional tree structure clearly discriminate in saying, although it is all a tree structure which is defined, the level of the tree or the height of the tree is reduced when we shift from a 2-dimensional tree to a point quad trees. There has been no change on the performance of both the things, but performance seems to be more heavy on the point quad trees, and the complexity also is comparatively less as we march towards higher cross section of the trees. Thank you.